Hello, and welcome to a special THWAC Camp session, NetPath, Every Node, Every Path, Every Network. I'm Head Geek, Patrick Hubbard. With me, of course, you know Leon Adato, also one of our Head Geeks.
Hi, everyone.
And I think every one of you know Chris O'Brien from THWAC. He is our product manager for NPM.
Hello.
We wanted to do this session after a lot of feedback that we got interacting with you guys at SWUG, at our SolarWinds user group meetings. Chris was doing a session that was helpfully entitled NetPath, How Does It Work?
How does it work, right?
And one of the things that we discovered in those presentations was that the audience was as interested about what we learned with the development of NetPath as the tool itself.
Yeah, we would be showing NetPath as part of our normal dog and pony show and things like that. And the very first question everyone asked in every single session was, how are you doing that? And they'd have their own theories, but they really, like, what's behind that? And so
you have to know. You have to know as a geek how it works.
Yeah.
Right,
yeah, definitely.
And you're fond of saying that in academia and some very large ISP engineers actually know how it works. But we have discovered that, at least I've discovered that a lot of the preconceptions I have about the way that the internet actually routes traffic are wrong.
Yeah. Through the development, we certainly learned a lot about how the internet works and how it doesn't work that we thought it worked.
And that was one of the things that's kind of interesting. You know, you were showing demos, early previews of what you were calling the lab widget or lab toy.
Lab toy, yeah.
A lab toy. And it took a while to build NetPath because I think you guys were actually sort of letting it find its own path, if you will.
That's right. I mean, the start of the thing was really that we had a shift in technology where applications were moving to the cloud. So whether that's Amazon or whether that's a SaaS app, applications that were in your data center were now in the cloud. So Exchange becomes Outlook 365. Now, under the hood, that's actually a lot of change in terms of the infrastructure to deliver that service. So all of a sudden, there's a whole bunch of companies involved, even companies you don't pay, like just random internet transit providers.
You're completely unaware of.
And so you depend on all of these for the service to work. So drastically different infrastructure, but what is definitely the same is the IT guys responsible for it. So what we had was situations where even at SolarWinds, we had services that we love and depend on, like Salesforce, go down or start acting slow, or worst of all, are intermittently slow for some people. And we go to IT and say, hey, you need to solve that. Now their visibility is completely different, but their responsibility is still the same.
Right, and I'm sure that when Salesforce goes down, you will never be called into a meeting to talk with people who are way above your pay grade and have a really difficult conversation.
Turns out people like revenue, so that's an important thing for all companies. So we realized, customers were coming to us and saying, hey, we've got all of these SaaS applications and we've got some visibility gaps. And so this is our job, is to provide that visibility. These are our guys. These are network engineers. They have a visibility problem, so it's our problem to go and solve.
And it goes back to what you said earlier about the unnamed, unknown carrier. It used to be if you had remote sites, you had a fairly good chain of throats to choke. In terms of from office A to office B, you knew how you were getting there, even if you had to call a LAC or whatever, but you knew where you were going. Now, with the SaaS and these other, there's all sorts of companies involved that you have no connection to at all. You can't find out. And I will tell you as a network engineer also, even that, old style office A to office B, that connection was still frustrating, but we sort of tolerated it. Now it's become intolerable.
Yeah. Definitely. So what we did, of course, is what we always do when we discover big problems. We take some of our best geeks, we lock them in a dark room, we provide plenty of Mountain Dew, plenty of pizza.
Yep.
Once we've got that very important infrastructure in place, we get to work, right? Work on solving that problem. So that's exactly what we did for NetPath. So we're here to talk about some of the lessons that we learned along the way.
Okay, so we are occasionally going to show maybe a screenshot to illustrate something, but this is not a how-to session. There are a ton of training videos that are out on THWAC in the Customer Success Center. Our lab episodes, we've done a couple of them, so there's lots and lots that'll do things like how to set up and config. This is about what we learned as a process of developing this. And I think the first one was actually about Traceroute.
Yeah, and really when you think about that problem area of troubleshooting, right? How do we do troubleshooting better, specifically in these new environments? What we realize is the one sort of core set of information you virtually always have, even when everything is going wrong, is you've got a path from one source to one destination that's not working properly.
Right.
So that was always like, how can we translate that bare set of information that you do have during the worst outage into what you need to start troubleshooting? So that's how NetPath was born, right? We make a path from the source to the destination with a destination port. That's the entry point. And we started with Traceroute, right? Traceroute does this. So that was cool.
It seems to do this.
It seems to do this. So what we did is we went and we opened our command prompt and we typed in Traceroute to some internet source or some internet destination. And we start getting results back. Our first hop is 10.111.8.1. Traceroute takes a little bit of time. This is not the most fun part of doing network troubleshooting.
But in the middle of a problem, this is the nail biter. This is where the music swells underneath. Right. This is where the tension rises.
But really quickly, it becomes unusable.
Yeah. So we got some asterisks here, which are shorthand for I don't know what's going on. And there's more of them. Turns out we block Traceroute at SolarWinds at the Firewall here, and most companies do.
Right. And 5 years ago, maybe not so much. 10 years ago, certainly not.
Yeah. So it turns out Traceroute doesn't work for us, doesn't work for most people. So that introduced our very first problem. Like we liked this mental model of, as a network engineer, you think, okay, I generate my packet from some source. It goes through a set of hops. Each one of those have some performance that I can measure, and then it gets to the destination. Fantastic. That's how networks work, right? That's how packet moving works. So there's a great mental model. It just so happens that Traceroute doesn't work. So what we had to do is go and figure out how can we start to get that information back and provide that path. And so that's where the problems began.
Okay. So you did a chalk talk about how you start to think about the way that Traceroute is returning data. So why don't you walk us through that?
Yeah. So I'm going to pull up our handy-dandy Blackboard here. And so the first thing to think about when you're thinking about Traceroute is how we come up with this list of nodes. And when we get by I guess before we even jump into that is the challenge of the firewall.
Right.
So what we realized very quickly is the way to get around firewalls is just to act like the application traffic, right?
TCP, port-specific traffic.
It's actually really simple. As soon as you act like the application traffic, then if the application works, you work, and if the application doesn't work, you don't work. Right. And that's what we want to be showing, right? So that was our first little indicator into the wisdom of how to really go about this, is to chase that network truth. Stop creating diagnostic traffic, just create application traffic and measure that. So that's what we started doing to get by firewalls. We act like application traffic. And the next thing to figure out is multipath, right? So multipath is super important on the internet. So you'll have, what you'll see in NetPath is something that looks like this, where you have a source represented as a box on the left.
Right.
That's your source computer. That goes and connects over to its default gateway. That connects, starts branching out. This is the multipath. So a portion of my traffic is going over that first path, and a portion of my traffic is going over the second path, the bottom path.
A lot of times asymmetric links.
That is possible. So you get some multipath that looks something like this, and finally somewhere along the way that gets to the destination. So I got my source on the left, my destination on my right, and some multipath to get there.
Right.
Okay. So academia has actually already figured this out, that multipath is super prevalent on the internet. Some 80% plus of paths that transit the internet go over multipath.
But that's the point of that. And what's different from our networks, we try to sort of condense down the number of links that we have, so there's less to troubleshoot, and it behaves in a more expected, easily understood way. But multipath on the internet is what makes it reliable and robust.
Right, and this is one of the hurdles, is that why we say that people typically don't understand the internet, because we think we do, because we understand our networks, and we think, well, it's routing and switching, right? But obviously, what's happening beyond your firewall, beyond your DMARC, is an entirely different world, in terms of what's important and what, has prevalence. So that's why we think we understand what's happening in the internet, but we actually don't.
With little to no control and still the same accountability to management.
And multiple handoffs. Oh yeah, right. And and multiple handoffs to people that you don't know and all of that, right?
Right. So big differences between the LAN side and the WAN side. You have the ability to make multipath LAN side, but on the WAN side, it's all about the multipath.
Right.
And much more, it's all about the layer 3, whereas LAN side tends to be more layer 2. So there's a lot of big differences that change how you approach problems when they're on the internet. Not to mention all the different companies involved. It's not all your gear. So that SNMP access doesn't really work anymore. Right. So when you think about how Traceroute works, there's some really interesting research on Traceroute. You can get a lot of information about Traceroute, but there's a lot of limitations too. So I would encourage everyone to look that up. It's sort of enlightening to figure out how Traceroute as a protocol works. But one of the basic things is, as Traceroute, I'm going to come up with a list of nodes that I go through, a list of hops that I go through. And how that works is the source sends some packet, usually an ICMP packet. It sends it with what's called a time to live, a TTL of 1. Okay, so this TTL thing is a mechanism to prevent infinite loops on the internet. So every time a router receives a packet with a TTL of 1, a TTL of anything, it decrements that value by 1, and then if that value has reached 0, the packet's dead. Time to live. That's how it works, right? So Traceroute works by sending one packet with a TTL of 1. It reaches the first router. The router decrements that TTL to 0. The packet is now dead. The router notices the packet is dead, throws it away. Loop averted, right? Once the packet is thrown away, it creates a brand new packet from itself back to the source, right? So it looks like that. So maybe this is your router 1, this is your router 2, this is your router 3, 4, and 5. So you get your first hop back, and that's when you see in Windows, Linux, Mac, whatever you're running, that your first hop, that's 1.
Usually a predictable hop.
Yeah. Yeah, and they'll have some metrics around latency and so forth. But anyway, we've identified that the first hop is 1. Now the second packet that comes out of your Traceroute implementation has a TTL of 2. So it reaches the first router, decrements to 1, then it goes ahead and forwards it because the packet's not dead. Maybe it forwards it to 2, this router 2 here. So that reaches 2, 2 decrements to 0, packet's dead, 2 creates a new packet back to the source. Now we have our second hop. All right, so we found our router 2. We've got our 1, our 2. Next thing, TTL 3, of course. So that may use this path, and we get a response. So now we have our 1, 2, 5.
What about routers 3 and 4?
So that's an interesting question. Actually, this presented an ideal scenario. So that's how Traceroute is supposed to work. Unfortunately, all of these separate packets completely separate and not a controlled function. Okay, and so what that means is, in reality, if we scoop some of these back out, we will see we'll do our first packet over on the left there, reaches 1, always reaches 1. Our second packet may go to 2. Our third packet, TTL3, may actually take the bottom path, in which case you're going 1, 3, 4, that's our third TTL, and then back. So now we've drawn our path as number 1, number 2, and number 4, and so on to the destination.
3's not even there.
3 is not even there. Now this is actually really, really confusing when you're looking at it.
Or you might get 1, 2, 4, and then 5.
Yeah, who knows? And so there's some really confusing things that are going on here. What it amounts to is Traceroute isn't designed to find distinct paths. Every packet it sends is separate, so it kind of mixes all of these paths together. So in your own LAN, where you don't have a whole lot of routing, you have just some, you don't have a whole lot of multipath, you can kind of get away with it. On the internet, it gets really confusing really fast, because all I see as a network engineer without this nice diagram that I actually don't have is, I have a path through 1, 2, 4. Makes 0 sense.
So not only are you not getting the information, not only is it blocked in the first place, even if it wasn't blocked, that still wouldn't solve this problem.
That's right. That's right. So what we did to solve that is basically figure out how routers were making decisions as to where to send packets, and make sure we stay on the same path when we go through the process of figuring out a single path. Easy enough, right? Okay, so now that we've understood multipath and we've discovered these paths, the next thing that we started to try and do is figure out how our paths were changing over time. And the challenge we ran into here is when you start comparing things, the need for accuracy goes way up, right? So as you move through each time slice, your expectation as a human is, I'm going to see only when things change. So we have to be really reliable in being able to discover all of the paths consistently so that we can discover there's 10 intervals with these 20 paths, multipath. There's lots of paths on the internet. 10 intervals or 10 half-hour periods, 10-minute periods that have these same set of paths, and then at one interval that changes, and then it changes back, right? And so we have to be able to present that reliably and consistently. So the next problem we had to find is, or we had to solve is, discovering these distinct paths, discovering all of them through the manipulation of what the routers use, how the routers determine all of their different paths, and algorithm we created to determine, okay, we've discovered, say, these 60 paths. How do we discover if that's all of the paths that are likely to be available? So when you put all of that together, we've accomplished path discovery. That's the first big half of NetPath.
And it takes a little bit of time. It's not like a regular polling interval where you go in one big ping that sends out a sonar wave all the way out and bounces off all the objects and brings them back. This is actually tracing these routes. It's starting looking like in this case with one, expanding its way out. It's modifying TTLs. It's simulating traffic, and it takes a little while so that it can get, like in this case, if there's a 50-50 chance that it's going to take this route between 1 and 2 and 1 and 3, you're going to have to send some traffic over that to identify that other one.
Yeah.
The way I like to tell people to think of it is, remember the Choose Your Own Adventure books. So the way that you're supposed to read them is you're supposed to, get to page 2 and read it, and see at the bottom you're supposed to go to page 42 or page 13 or whatever it is, and you go whichever path you want. Well, now what you want to do is have a little notebook, and you want to say, 13 and 4, and then you start to map out all the possible combinations and visualize all that. So now you know all of them, and then you go back and read the book and say, this time I went this way. Last time I went this way, and all the choices that the packets are making as they go. So in case that helps.
Yeah, you are such a geek.
I'm sorry.
It's very geeky. Right. So speaking of that brings us back to, okay, so we've got our path discovery. The next step is to determine status, right? It turns out like we came up with all this data, we were very excited, then we showed it to customers and like, wait a second, what's red? Right. What's yellow? What's green? So we've kind of set this expectation at SolarWinds that we're always going to present an intelligent but simple conclusion. Is this thing red? Is it green? Is it yellow? So that actually became the bigger challenge for us. And it took us a long time to start figuring that out. And what I like about what you said is, as we were thinking about this and sort of going with the wisdom that had taken us through path discovery of thinking about what is the network truth here, we realized the picture that we were trying to show is the complete experience. And what I mean by that is when a user over here on the left side creates a new connection, it could take any of these paths. If you have 20 users, it's probably taking many or most of these paths. But what we need to express in this graph is the complete delivery path from the source to the destination. So we need to find all of those options in the Choose Your Own Adventure, Choose Your Own Router book and be able to display all of them at once and figure out how many of your people are going over the top path, how many people are going over the slow path, how many are headed for a cliff, and present that as a single holistic picture of the delivery path from source to destination. Okay, so we've discovered our path. We're working on path performance and analysis and figuring out that simple, intelligent conclusion that we can present. Is it green, yellow, or red?
Right.
So the first thing when we first started presenting these paths and finding them, what we quickly realized is the WAN links are always red. Of course, they're the long ones, right?
Compared to the time for everything inside the network,
That's
they're
right.
really, really
like
long.
if I've got two routers in the same closet, they speak to each other in 1 millisecond, probably less than 1 millisecond. That is always going to be much, much lower than when you have a link that's going across the US or going on an undersea cable or what have you.
Right.
So we again started thinking about what is the network truth here. Just because something has latency does not mean that thing is unhealthy. Right? That was the fundamental flaw in our thinking initially, where we just had, okay, everything has a threshold of 200 milliseconds or what have you, or 50 milliseconds.
Right. Again, the difference between we know the internet because we know our own network and realizing that set of knowledge does not transfer.
Yeah, that wasn't enough. So what we started thinking about is, okay, so what is healthy and what is unhealthy latency. And in thinking about that, what we realize is, thanks to the fine guys over in QoS, they figured out a lot of this for us, which is when you look at the delay imposed upon a packet, the delay or a frame, the delay is always in one of a couple of buckets. Let's see if I can remember them all. The first one is serialization, there's propagation delay, there's queuing delay, and there's processing delay.
Right.
These are the 4 buckets. All of the delay for every path or every network connection everywhere fits into one of those 4 buckets. And when you think about that, propagation delay really has to do with speed of light. Doesn't really change much.
It's distance.
That's right. And in today's world, serialization delay, first of all, it doesn't change much. And the other thing is it tends to be a very finite, very small portion of the delay. So those are not where unhealthy latency comes from. When you have unhealthy latency, it's because of queuing delays with QoS, or it's because of processing delay for the device processing the packets, right?
Overwhelmed CPU.
That's right. So you've really got, out of those 4 buckets, you've got a bucket where you get healthy, where unhealthy delay does not show up, and a bucket where unhealthy delay does show up. So we really focused on figuring out how we can identify which bucket the latency is in. So on any link, we can determine how much of the delay that we're seeing is healthy and how much is unhealthy. And then we compare those 2 values. Like, is the latency here 50% unhealthy?
Right.
That's probably a yellow or a red link. Is the latency here 5% unhealthy? So there's just a slight variation. That's no problem. And so applying this same logic to your WAN links and your LAN links allows you to start to figure out which one is actually unhealthy.
300 milliseconds total end-to-end latency. 200 milliseconds of that in the middle between 2 hops is rock steady at 200. That is not unhealthy latency. That's just the distance for that link.
Maybe satellite or whatever it is. I don't know what it is, but
another link in there that's actually 5 milliseconds suddenly hops up to 10. That's a problem.
Yeah, and so if you think about that, you've got 200 milliseconds of WAN latency. You've got 100 other milliseconds of stuff. Maybe that's your LAN. Right? And so we've determined that that 100 milliseconds, that's way more than we would have expected, that has a lot of unhealthy delay. We'll call the WAN that is lesser of the total delay the red thing, and specifically down to the link. So actually, we should take a look at some of what this looks like. Okay. So we're on the NetPath services main page, and we're monitoring these services over on the left. And you can see from Yahoo, we're monitoring from our Austin office, Brno, and Singapore. Like, service is different for all of these sources, right? Sure. And to all of these destinations. So it's important to understand all of that.
And there's no probe installed out in Yahoo. We're doing this entirely from inside our building.
That's right. That's right. The probe is always at the start. So we'll click on the Austin office. We can see at the top left, orienting ourselves to the picture, this is the Austin office to Yahoo. And over on the extreme left side of the page, we have our source probe. That's where we have the NetPath agent. On the extreme right, we have the content servers that are providing yahoo.com, at least in this region where the probe is at. And in the middle, we have the path it took to get there. So pretty quickly here, we can start to see there's a number of companies that we depend on for this path to function. Okay, so we've got quite a few links here, and let's actually start blowing this up and thinking about that healthy versus unhealthy delay. So I'll pop open Time Warner Cable's 2 networks, pop open EXO Communications. We'll take a look at Yahoo, and actually let's look at both of Yahoo's now. Okay, all right. So now we're starting to see what the internet really looks like.
It's a little messy.
Turns out the internet is complicated. So the first thing you notice is...
Or at least Yahoo's complicated.
Yes, Yahoo's complicated. Now, when you think about delay here, we have hop-by-hop performance. That's really important if we're trying to isolate where the problem is. It's not good enough to say what the end-to-end delay of this path is. We have to figure out exactly where the delay is. So, for example, this link here between this router owned by EXO and this other router owned by EXO, 7 milliseconds of delay imposed specifically by that link. Meanwhile, the EXO router connects to a Yahoo router, and that connection imposes 23 milliseconds of delay. So this unhealthy and healthy latency was also important because think about how you would apply thresholds to this path. How would you do that? If you wanted to figure out which thing was red, there's like 50 or 60 nodes on here, and many more than that connections between nodes.
You would never have time to manually set all those thresholds.
No. And this is the internet, so tomorrow it's going to be all different,
Right.
right? This is a constantly changing thing. So that unhealthy and healthy thing is something that has to happen completely automatically, which of course it does. That's how we built it. So the next thing to notice is, let's take a look at actually some simple multipath here. So this is just too confusing. So we're gonna pop these back down, summarize them back down, and we get our much more easy to understand picture of, I go through my network, then I go through Time Warner, EXO, Yahoo, and finally reach Yahoo
You've just
servers.
collapsed the groups down.
That's right. So let's go ahead and take a look into Time Warner Cable's network. We see 4 paths here. Now these paths all have 1 millisecond, and there's actually some slight variation. This link is taking less than 1 millisecond, while this link is taking a full 1 millisecond.
Okay.
So each one of these paths is going to have slightly different performance. And if you mouse over these links, what you'll see is a portion of your traffic goes over each path.
Right.
So 29% transiting this top link, some 20% this link, 25%, and so on.
That's at transit likelihood percent.
Transit likelihood. So how much of my traffic is going over this specific link? And that's important because it's important to understand when there's intermittent behavior. This is actually the root cause. This multipath thing is oftentimes the root cause. So someone comes to my desk.
Or you're sitting there running a ping.
That's right.
And you're watching it wobble.
Yeah, and you're like, what's causing that? I guess it's just one router acting erratically, but that's not oftentimes the case. These are separate packets, they go on separate paths. And so when someone walks up to my desk and says, hey, this service is sometimes slow, I can then go look at NetPath and determine, hey, I've got a 20% or even a 5% transit likelihood link that imposes 200 or 500 milliseconds of delay. So it really allows you to pull apart and piece apart those different sets of delay.
So there's really annoying long tail help desk tickets where there's just a teeny number of users who are suffering something horrible and usually escalating that through email and saying, you are not solving the problem, and you're looking at your regular dashboard saying, I do not have a problem. 99% of the time, this is entirely fine.
And you're trying things, you're trying to fix things, and it clears up because, of course, now they're taking a different path.
Yep.
And then tomorrow, it's like, it's back again.
Yeah.
It's not back again, but...
Extremely frustrating. And so we thought again about, okay, so this actually imposes a new problem, right? So say this top link is 20 milliseconds, and the second link is 100 milliseconds, just for example.
Okay.
Which of those 2 links should be read?
The one that's normally out of its...
I was going to say... Good, sorry.
No, I was going to say the one that is exceeding its normal baseline.
Yeah, it's monitoring on a delta, which a lot of people don't think about. It's not monitoring on a threshold, a set fixed thing. It's monitoring on the difference between normal and what it is right now.
Yes, and we need to be careful here because it is healthy versus unhealthy. So one of the challenges was on our very first time discovering a path, we need to be able to detect a problem. So baselining doesn't work. So what we usually think about as the way to solve this is baselining. That couldn't work for us because we couldn't figure out what the problem was right now, so we didn't.
Right.
And that's just not how it works. It's really that healthy versus unhealthy. So going back to my challenge of like, which one of these do you call red? I forget which number I used, but in any case, it's always the same, which is you have the degree of unhealthiness, right? And then you also have how much of my traffic moves through that link, right? So if I've got this link that is, let's say they're equally unhealthy, but 80% of my traffic goes through that top link, the intelligent, simple conclusion we want to present to users is that top link is the problem, that top link is red. Okay, so we have to...
Because it's having a disproportionate effect on the overall application traffic that's transiting all the possible paths.
That's right. So we had to solve figuring out all of the paths, right? Consistently figuring out all of the paths, then figuring out the performance of each hop, then figuring out what is the healthy versus unhealthy latency, so we can figure out what in here is unhealthy, then correlate that to how much of my traffic is using each one of these components so I can understand the impact to end-to-end performance.
Well, and then there's another thing here that you mentioned in the Chalk Talk, and it's something that I knew about theoretically when I was thinking about a router, but it didn't occur to me as a problem with Traceroute or a couple of other protocols, is that using TTL as a probe technique is inherently unstable because of an ASIC effect. right?
That's right. That's right.
So you talk about that a little bit, because I know, when you run a traceroute and it's like, I just keep getting these different numbers. I'm 5, 4, 7, 55, 4, 3, and then the next time I run it again, then there's this other outlier where suddenly I'm 45 milliseconds and everything else is an order of magnitude smaller than that.
So it's painful. What's the challenge with it is you will get a path like that where it's these like various low numbers, then bumps to a high number, then bumps down to a low number, and then continues on, right? And those of us who haven't been fortunate enough to get paid to spend hours and hours researching Traceroute, I don't know why they pay me for this stuff, are able to interpret that and understand what's going on, which is that the outlier there is not actually a problem. Because you could get past that router and receive good performance, the next node was 7 milliseconds, not 50, then that means that router that looks slow is actually transiting traffic at a good rate. So what this is the difference between control plane delay and data plane delay. So router tends to handle its main activity of taking packet from interface, sending packet on other interface through ASICs, what they call ASICs, right? Application-specific integrated circuits that are custom-designed hardware. All they do is move packets in a very specific way.
When everything's working as expected.
That's right, when they're transiting, right? But these TTL expiry packets are different. So the problem there is the router takes the packet, throws it away, then it has to create a brand new packet. And it has to do that in a way that's like it's not transiting data anymore. Right. So then it oftentimes, sort of depending on the hardware, requires a CPU or a different piece of hardware to get involved. And then you've got a big problem, which is the behavior of the diagnostic traffic is significantly different than the behavior of your app traffic. And you really only care about your app traffic.
You're introducing a moment of compute latency delay.
That's right.
Instead of just routing delay.
That's right. So when a network engineer sees that high spike, they think the problem's right there. In reality, oftentimes the problem is not right there.
And I'm willing to bet crafting those X-ray reply packets is not high in the priority for that processor.
Yes.
So as the traffic is changing across the interfaces of that device, it's going to be returning different, wildly varying latency times for its return on that packet.
Yeah. So it gets really complicated there, and when you get this degree of, like, we're trying to show hop-by-hop performance because that's necessary for problem isolation. And to do that properly, we have to go and figure out which of these delays, it goes back to that healthy versus unhealthy. Which is unhealthy, which is healthy, which is a transit delay, which is a control plane delay. And we really remove all of the control plane delay here. What you're seeing is your data plane delay because that's the network truth for your application. That's what you care about, right? So that's a lot of the sort of thinking and some of the problems we've had, specifically around latency. And so, like, when you think about the whole picture, you get this end-to-end set of paths,
right,
and they deliver an end-to-end performance. That's what you see across the
Because it's not just the internet. It's not just the internet routing, it's also your local routing as well, and being able to troubleshoot that a little bit easier.
That's right. So if we jump back to NetPath services, we'll start seeing what sort of this looks like in a real troubleshooting scenario. So we'll take a look at Salesforce. You remember I said that was important for us? So we tend to...
It is important for everyone. It's funny when people talk about that, they'll say, you know, we're using cloud, we're using Salesforce. It's like, is that really cloud or is that SaaS?
It's whatever you want to define it as. It's, you know what, we're using it and it's important to us and we'll call it whatever we want to.
But they'll describe Netflix as a service, only that actually is cloud.
So troubleshooting these things, very challenging. This is a path that we have in our environment. We see our portion of the path on the left side, some companies in the middle, and then across the bottom, we have that end-to-end performance that's considerate of how much of my traffic is going across each one of these paths. What is each path's latency and packet loss performance? And so we can see around 3:50, 4 p.m., there was a spike. So at the time of the spike, if we click that value, we can go back in time and look at what that was. So here we see significant increase in delay, NetPath is telling us, specifically with this link. This is the only link that's red. That's where my problem is. And it appears to be related to this configuration change. So we found there was an increase in delay, and there was a configuration change around the same time that occurred on the device where the increase in delay is happening. And so that's why we're showing this here. And clicking on that will answer the question, okay, so what was that configuration change? And this is diff coming from our NCM tool. So we can see there's a traffic shaper change.
Misshaping change.
Yeah. Yes.
It's a fat finger, I added an extra 0 change.
Right.
Is really what.
Now, one of the other things we start to notice here is it's really important to start to do comparison. Comparison is an extremely powerful tool when you're troubleshooting. So it's one thing to figure out when a problem occurred, or start to investigate what the configuration was at the time. It's a whole different thing to say, okay, problem occurred at 4 p.m. How did the network look before that? In terms of both performance and configuration.
Especially just before, right?
That's right.
To be able to say, I could look at any result back in the past, but how do I even figure out where that change happened and get the last good configuration, if you will, the last green configuration.
That's right.
The last good moment.
Yes.
So if we look at our timeline across the bottom, we can see that the last green interval was right here. So we'll click on that interval and it'll pull up the graph for that portion. So in this case, the entire graph is green, of course. Right? That's why the interval is green or good.
Right.
So here we're seeing 3 milliseconds between our R3 and our R5. And at the peak of the problem, click on that and that'll load up for us. Between an R3 and R5 went to 234. So definitely that's where the problem is.
Again, monitoring based on the delta off of what we're seeing.
That's
not
right.
Just
That's right. So the last thing I want to talk about before we talk about some of the sort of the next step that we also didn't expect is packet delivery and packet loss.
Okay.
So how we have thought about packet loss as network engineers is there's a percentage of packet loss. We all know what packet loss means. Now when we were building out NetPath and trying to explain what's going on with this path and how users are reaching apps and what their performance is, we started to realize there's a lot of ways you can lose packets, and they don't actually all feel like they're supposed to be called packet loss. So if I put in here www.salesforce.com and I can't resolve salesforce.com, is that packet loss? That's not called packet loss, is it?
Right. It's just you usually can't resolve it. DNS is available for that.
That's right. There's what packets were lost? None.
all of them, because you sent them to the wrong place, or you couldn't get where you wanted to go.
Right, or you couldn't create them
in
in the first place because there's no IP to send to. So that's a different thing from packet loss, but it kind of is packet loss. And there's lots of reasons that could happen. What if you send a packet and it makes it all the way to the destination, but that destination has its port closed? Well, certainly that's not packet loss. The packet made it all the way to the destination.
The firewall might be doing exactly what it's supposed to do on the other end. It thinks you're doing something nefarious and it just drops it.
Yeah,
That's
but
right.
this goes back to what you said at the very beginning, which is that what we started with was a starting point and an end point, a destination. If you don't have those two things, you don't actually have a path.
That's right. But in this case, it reached the destination, right? It reached the destination in the port. When I say port, I should have been more specific. The TCP port on that, for example, Windows host is closed. So as far as the network is concerned, that is absolutely not packet delivery.
Yeah.
But the problem is that the application certainly, if that's a host-based firewall, the application doesn't think that packet was delivered. So there's lots of different reasons there. So what we had to do is come up with something that we call packet delivery rather than packet loss. How well are we delivering packets? So that doesn't suggest that a specific router is losing the packet. And then we had to take all of these various sources of decrease in packet delivery and put them all together. Because if I'm experiencing 5% real packet loss and sometimes my DNS every once in a while doesn't resolve and every once in a while the port is closed, the service to my end user may be that 30% of my packets aren't being fully delivered to the app.
Meanwhile, most users are reporting that it's working fine.
That's right, but 30% is still completely inappropriate.
No, absolutely.
Right? So we have to combine all of these different sources for potential non-packet delivery, right? And use that as the thing that we measure to determine if it's unhealthy or healthy in terms of not the latency or the delay, but the delivery percentage.
Yeah.
And then again, percentage through what through what link, through what node, all of that stuff still comes into play. So we have to do all that math to figure out the end-to-end relationship there. Okay, so one more thing you may have noticed here, and that we realize is, hey, we've got some routers and we've got some other stuff at the beginning. Now, in our early versions, we were using one set of technology, our early prototype. We used one set of technology that discovered the entire path that we built from scratch, right? And we custom craft these TCP packets through a Windows packet driver and all of this sort of stuff, and we come up with this path. Right? And we get some really cool information, particularly about the internet nodes. In addition to the pathing and performance, we get things like who owns that node and how they're doing some of their routing and what their contact information is when there's a problem.
And that was the one that was interesting. We had beta customers, who were identifying that there were, for very large telcos, there were people's cell phones and their names listed as some of the contact information for some of these publicly accessible routers.
That's right. And one of my favorite ones is the guy said, hey, I know that phone number. That's my boss's phone number. Right? So some very interesting information there. But when we sort of put that all together, we had a picture that was felt like very full on the internet side, but the nodes that we had the least information about were your nodes.
Even though you're already pulling them with other technology.
That's right. And we're like, wait a second, we're SolarWinds. We know a thing or two about those nodes.
We've got to get that in there.
Right. So we took the time to sort of start pulling in all of that data and enriching the picture on the LAN side with everything we know about those nodes. So here on the left, you see this is my R1. And we're calling that R1 because in NPM, in Orion, you're calling that R1. Okay. So this is your preferred node name as the administrator. That's what you call it. That's what's most familiar to you.
That's what'll show up in NPM's main panel. It'll show up as, router name Pookie or Schnookums or whatever it is.
That's right.
Yeah. You have some adorable routers.
I do. They're cute.
So that's distinctly different from just getting reverse DNS, which is its own value set, but again, different for internet versus LAN. Okay. And so you have your node. We also have the node role. If that's my network, it's super important for me to understand, is that a router? Is it a firewall? Is it a multi-layer switch? Right. What is the function of this device in my network? So we showed that in the picture in the middle. In this case, it's all routers. When you hover over, you start to get what type of router this is. So this is a Cisco 7206 VXR. We've got different CPU, RAM, and all of that data. We also map out to the interface, down to the interface. So this top link is running poorly. That comes into my Ethernet 1.0. The bottom link that's running fine, that goes over Ethernet 1.1. So I really want to focus on that Ethernet 1.0 through that mapping.
Okay.
Right, because ultimately, again, we're trying to help our customers fix their problems, and the more we can tell them about how everything is going through, the faster they can get to either what I affectionately call MTTI, mean time to innocence, or to actually get to the problem.
Okay, but you're doing some other things on this, the interface, like you're doing a NetFlow export so that you can actually see what that traffic looks like.
Yeah, so if we go through this end-to-end, right, we have discovered the difference in our end-to-end performance. We click on the red to find what was going on at that time. We see NetPath has identified specifically this spot is where the red is occurring. We know more about those nodes. We can click and get the configuration change. If we want to change that, we can use NCM to revert, or we could also inspect the interface deeper and actually look at flow data. So that's data from NPM, data from NCM, data from NTA, all the things you need to know about performance, config, and the traffic flowing across your network to solve this problem.
And in this example, this is a misfeature for traffic shaping, right? Where you've applied a throttle effectively. That router is doing exactly what it's supposed to do. But if I'm polling that router with SNMP, it's going to tell me that maybe the interface utilization is 5%. It is behaving itself. My alerts are not going to trip. There is nothing wrong from a polling perspective. The application is having a problem because I've misconfigured my traffic shaping in that config.
Yep, that's absolutely right.
I can solve that before my boss finds out.
I hope.
This is so exciting. I feel like I'm looking at the secret life of packets here. And what's also exciting about it is it's really new. I mean, as you said before, it should feel like this, but it hasn't. This is the first time I've seen something like this.
Yeah, it looks different because it is different. That's not what we set out to do. We were just trying to solve a problem. But at the end of the day, this is something new. And what's really exciting is now that it's in front of us, it's like, well, this is how troubleshooting should feel like. It's like, This is obvious. Why hasn't it always worked like this? Of course, I should see a map of my path and figure out where the slowness is and have time travel controls and have all of my data about one problem or one outage in one spot. Of course.
Yeah.
Well, Chris, thank you so much for coming and talking to us about this. You guys who've been coming to the SWUGs have had a chance to hear us talking about this a little bit. The last time in Atlanta was the first time that I'd seen you do the Chalk Talk. It was really, really informative, and thanks so much for coming.
Happy to do it. I love talking about NetPath.
Awesome. Well, we hope you all have enjoyed that. Please keep your questions coming and enjoy ThwackCamp.